Well, good afternoon, ladies and gentlemen, and welcome to the Symons Gold Medal Lecture. The Symons Gold Medal was established in 1901 in memory of George James Simon, FRS, a British meteorologist who founded the British Rainfall Organisation. The medal is awarded biennially for distinguished work in connection with the meteorological science. The medal ranks alongside the Mason Gold Medal as the premier award of the Society and is bestowed in alternate years to the Mason Medal. Now, this year's, or the 2018 Symons Gold Medal is awarded to Dr. Clive Rogers, who will be speaking to us shortly, for his seminal work on atmospheric remote sensing, including the related fields of atmospheric spectroscopy, retrieval theory of satellite data, remote sensing of atmospheric temperature and composition, and the design of satellite instruments. His work has had a profound effect on the exploitation of satellite data across atmospheric scientific disciplines, both in research and in operational weather forecasting. His lecture will trace the development of remote measurements and data analysis methods over the last 100 years. It is therefore with great pleasure that I invite Dr. Rogers to deliver the 2018 Symons Gold Medal Lecture. Thank you.
Thank you, David. Good evening, ladies and gentlemen. Firstly, I would like to say how honoured I feel to have been awarded the Symons Gold Medal by the Society. When I looked at the list of eminent scientists who have received this medal, I feel sure I really don't belong in their company. As this is the Symons Memorial Lecture, I will begin by saying a few words about who he was and what he did. If I can get this to work. Okay, got it. Got to press the right button. George Symons, FRS, was an enthusiastic scientist from a young age. He joined the Society at age 17. He was a council member and secretary, and he was president twice. He was most well known for establishing the Rainfall Network with over 3,000 volunteer stations, and for setting up the Meteorological magazine. But there were many other achievements that I really haven't got time to summarise. He was elected president for the second time in 1900 for the 50th anniversary of the Society, but illness prevented him from acting, and regrettably he died shortly afterwards. The medal was established in 1901 in his memory. It was first awarded in 1902 to Alexander Buchan, a Scottish meteorologist who is credited with establishing the weather map as a basis for forecasting, and who was the president of the Scottish Meteorological Society for many years. Moving on to my subject, weather measurements had been made regularly at the surface for a long time, but little was known about the atmosphere above, apart from what could be obtained from pressing the wrong button again. Apart from what could be obtained from mountain measurements and from kites until the era of ballooning. The first recorded kite measurement was by Wilson and Melville at the University of Glasgow in 1749. They flew a train of kites with thermometers up to an altitude of what they called the white summer clouds. I really haven't got much idea how high that would be, but perhaps around 1 kilometre. Ballooning started soon afterwards, much earlier than I remembered, in the late 1700s. And scientific ballooning, I thought, seemed to have started with James Glaisher, who was a founding member of this society. But his book is on the desk outside, and I've been reading it while I've been waiting, and it started somewhat earlier than that. He and Henry Coxwell made numerous balloon ascents in the 1860s, as did other scientists later on, such as Richard Assmann in Germany in the 1880s and 1890s. They made in situ measurements of temperature and humidity. Glacier reached a record altitude of more than 8.8 kilometres and possibly up to 11 kilometres on the 5th of September 1862 from Wolverhampton, apparently somewhat accidentally because James Glacier passed out on the way up and Coxwell had to pull the release cord with his teeth because his hands were getting too cold to use. An early gold medalist, Tesseract de Bort, was active in sounding the atmosphere in the 1890s. He started making measurements from kites, carrying self-recording instruments, with which he reached around 5 kilometres. But he had various technical problems with these, especially with breaking cables. In one notorious instrument, an array of kites launched by Tesseract de Bort broke loose and drifted across Paris, trailing 7 kilometres of wire. They disrupted telegraph and train communications with Rennes on the day when the results of the Dreyfus court-martial in that city were awaited. He switched to using balloons completely. De Bort was co-discoverer of the stratosphere with Richard Assmann from Berlin, who was using manned balloons at the same sort of time. But in situ measurements are limited. You need physical access, so you can only cover a small number of locations. Remote measurements, especially from satellites, have many advantages. The first remote measurements from the surface, that is, that I can find, seems to have been around 1920, when Lindemann and Dobson measured air density, making use of meteors. They wanted to see if they could gain any information about the atmosphere above the lower stratosphere. They realized that they could estimate the density of the air at the heights where meteors are seen using a theory of the ablation of material at high velocities. Denning and his co-observers had been making measurements by triangulation of the height of appearance and disappearance of meteors. And using these observations, Lindemann and Dobson calculated the density of the air at these heights. It was generally thought at that time that the air above the tropopause was cold at all levels, and when the densities calculated on this basis were compared with those from observations of meteors, it was found that the two agreed fairly well for heights up to about 50 kilometres. But at heights above, the densities from meteors were about 100 to 1,000 times greater than they expected. The crosses on this plot, which was made by Dobson, are densities at appearance, and the dots are densities at disappearance. The larger crosses correspond to observers thought to be more reliable. To quote Dobson's History of Atmospheric Ozone at Oxford, "When I first showed the plot of densities obtained from meteors against height to Lindemann, with its large differences between the calculated and observed values, he immediately suggested, 1, that the air above 50 kilometres must be much warmer than was thought, and 2, that this high temperature might be caused by the absorption of solar UV radiation by ozone in the upper atmosphere." And he was right, of course. At this time, it was known that ozone existed in the atmosphere. It had been seen in stellar and solar spectra, but it wasn't really known whereabouts. So Dobson became very interested in finding out more about ozone, and he designed spectrometers to make measurements of ozone in the atmosphere. He discovered that there were day-to-day fluctuations in the ozone amount over Oxford, and that there was a regular seasonal variation. He hypothesized that the variations in ozone might be related to variations in the atmospheric pressure. And to test this idea, he had several more spectrometers constructed and distributed throughout Europe. These measurements demonstrated regular variations in ozone with the passage of weather systems. His second design was photoelectric and was built in a homemade wooden case. After his death, we had his observing hut on the roof of our building in Oxford, and we used it regularly. The rectangular one in this slide here is, I believe, a prototype copy made for him by Beck's, the instrument maker. The others are the final version of the ozone spectrometer made for the network. The network expanded worldwide for the IGY in 1957, and its descendant, NDACC, the Network for the Detection of Atmospheric Composition Change, is still using Dobson's today with various updates and improvements. Total ozone, whoops, back one. Total ozone was measured by looking at the solar spectrum. Goertz in the Rosa found that by observing solar ultraviolet scattered from the zenith sky as the sun set, he could determine something about the vertical distribution of ozone. He made measurements of the ratio of the intensity of scattered UV from the zenith sky at two wavelengths with different absorption coefficients. Throughout the day, he noticed that the ratio of the higher to lower coefficient decreased as the sun set. Then, just as the sun was nearing the horizon, the ratio turned around and started to increase. He called this the Umkehr effect. The physics was complicated, but the shape of the curve depends on the amount and the distribution of ozone. However, the interpretation of the Umkehr curve in terms of the ozone profile was not straightforward. Goertz, Meatham and Dobson, publishing in 1944, used a trial and error method, as did Karandikar and Ramanathan in India. They assumed a layered atmosphere and calculated an Umkehr curve according to simplified physics, then varied the amounts in the layers until they found a reasonable agreement. It was Hans Deutsch in Arosa who first developed a computer algorithm for Umkehr. He linearized the model equations and tried to solve for 9 layers, and then recompute the full equations and iterate until he got convergence. He found that the equations were too ill-conditioned to solve for ozone distribution by using one set of 9 linear equations. He thought it was, quote, because of the inherent accuracy of the measurements and especially because of the effective non-linearity of the problem. This wasn't the only reason, but we'll come to the real reason, underlying reason later. What he finally did was to solve for 2 sets of 4 to 5 linear equations of thicker layers for ozone, and in the two sets were overlapping layers, and obtained a final distribution of 9 layers by taking means of the 2 5-layer solutions. Satellites became a possible vehicle for atmospheric measurements in the late 1950s. As instruments were developed and new ideas generated, Gene King proposed that the temperature information could be obtained by measuring the angular distribution of thermal radiation from a satellite from various gases. He suggested using a filter radiometer with spectral bands at 6 microns for water vapor, 9.6 for ozone, 11 microns to see the surface, and 15 microns to measure temperature. He showed how to set up linearized equations with a small number of layers to derive the temperature from these measurements, but he didn't actually present any calculations. This was a conference report, and it didn't get much immediate attention. Quite separately, a few years later, Lou Kaplan, who seems to have been unaware of King's paper, realized that the spectrum could provide information about the temperature. He too suggested looking at the water, ozone and CO2 bands and at a window. He proposed looking at several spectral locations within a band where there are different absorption coefficients rather than at different angles. But he didn't make any suggestions about how to process the data. But other people quickly took up the challenge, particularly Dave Walk and Gichi Yamamoto. Dave Walk developed a simple way of interpreting the data. He set up a trial atmosphere with 2 layers and temperature defined at 3 levels. And he used simulated measurements at 3 wavelengths of 680, 690, and 695 wave numbers. He used target profiles, the dashed lines in these plots, at different levels, defined at different levels, and did simulations by linearizing the equations of radiative transfer and solving simultaneous equations. This showed that remote measurements done this way might be feasible. Yamamoto did something similar, but he tried various kinds of polynomials and used 4 radiances. If this plot of his test looks slightly unfamiliar, it's more recognizable this way up with pressure in the vertical, or log pressure in fact, and temperature, or linear and Planck function horizontally. Neither of them did a serious analysis, just demonstrations of feasibility. Here the solid line is a test profile, and the smooth lines are various different kinds of polynomials he fitted to it. It was round about this time in 1960 that I went to Oxford as a postdoc to work with John Horton on this problem. I started out approaching the problem just the same way that Walk and Yamamoto had, and came up against the same difficulties on trying to use more levels. But nevertheless, these suggestions were quickly taken up, and experimental sounding of the atmosphere from satellites began in 1969. The first sounding satellite was Nimbus 3, and this had 2 sounders on board, IRIS and SIRS. Here we have Nimbus B in the test chamber with its 2 sounders. Incidentally, satellites were denoted by letters before launch and numbers after launch, hence Nimbus B, not Nimbus 3 at this point. It was launched in 1968, but unfortunately the launch failed and it ended up in the ocean. But there were enough spares to build Nimbus B2 fairly quickly, and that was launched in 1969. That became Nimbus 3 rather than Nimbus 2, because the Nimbus C spacecraft was launched in 1966. It had somehow managed to overtake Nimbus B in its design and build phases. I don't remember how. The satellite, incidentally, was retrieved from the ocean because it had a radioactive power source, and they couldn't leave that down there. I was shown the remains of SIRS by one of the engineers who had it at home in his garage. Those were much more informal days. IRIS stood for Infrared Interferometer Spectrometer, and that measures the Fourier transform of a spectrum. This means that after transforming back to spectral space, we get a complete spectrum of the part of the spectrum it's looking at, in this case the thermal infrared. It had 5 wave number spectral resolution. Consequently, it had around about 2,200 spectral points across the spectrum. It made measurements looking straight down every 100 kilometers along the sub-satellite track. Various interesting points to be seen here. And what we've got is the spectrum plotted against radiance, but with curves of Planck function as a background. And you can see the temperature in the Sahara around about 320 Kelvin, the temperature in the Antarctic around about 190 Kelvin. You can see the carbon dioxide band at 15 microns here, and you can see water vapor lines pretty well everywhere, with a small amount of methane just here, and the ozone band here. This single spike in the middle of the carbon dioxide band isn't a water vapor line. That's a carbon dioxide Q branch, which is a very strongly absorbing part of the spectrum. The radiation either side of it is coming from the lower stratosphere at a temperature of around 220 Kelvin. But right in the middle, the radiation is coming from higher up in the stratosphere. Oh, back one. RS was flown on many satellites, including Nimbus 4, Mariner 4 to Mars, and on both voyages on the Grand Voyage. These retrievals of temperature and ozone were made using about 10 spectral intervals in the appropriate parts of the spectrum, and show that the concept is working to a useful accuracy. SIRS, Satellite Infrared Spectrometer, was a grating spectrometer with eight channels, using 8 detectors at different points in the spectrum. Its field of view was about 220 kilometers along the suborbital track, and these weighting functions indicate the range of heights which contribute to the measured radiance for each of the 8 channels. For example, channel 8 in the middle of the CO2 band is receiving information from higher up in the stratosphere. Channel 2 is receiving information from the troposphere, providing you can see it when there are no clouds. These are the locations of the SIRS spectral channels. This is a window channel, channel 1, 1, 2, 3, 4, and so on, down the edge of the CO2 band, and channel 8 in the middle. These retrievals show that SIRS also did a good job. The left-hand plot is the first retrieval made, compared with a radiosonde at Kingston, Jamaica. The smooth profile is the temperature retrieval, and the dotted one is the radiosonde. The not quite so smooth bit at the top is suspicious. It should be smoother. SIRS also flew on Nimbus 4. After this, there are too many satellites and remote sounding instruments to describe them all. I'll just talk about the main innovations and some of the instruments that pioneered them. Some of the innovations were, of course, standard lab techniques, but there's always a first use in space. And most of the innovations were followed by more capable versions using the same technique. I won't read through this list because I'm going to put up a slide about each one, or most of them, in what follows. The backscatter ultraviolet spectrometer was first flown on Nimbus 4. It uses the same principles as UMCARE, measuring scattered solar ultraviolet, but it uses several different wavelengths rather than several solar angles. And this is a set of weighting functions showing that it will see ozone from low down, if it's clear, up to around about 55 kilometers. BUV flew on Nimbus 4 in 1970. Its follow-on SBUV, Solar BUV, flew on several satellite and shuttle missions, and its successors are still flying on the current operational series, just like the Dobson spectrometer from the 1930s, which is still in use today. This is a recent plot of SBUV for the Southern Hemisphere. I'm afraid at the moment ozone isn't doing anything very interesting, nor is it doing anything very interesting in the Northern Hemisphere, so I can't show you an ozone hole or anything like that. This was 2 days ago. Back to history. As well as spectrometers, the other main instrument for measuring radiation is the filter radiometer. With Nimbus 4 in 1970, John Horton in Oxford got into the business with Des Smith, then at Reading. The method they developed to use with a filter radiometer was called selective chopping or gas correlation. The filter radiometer is very simple. It consists of a telescope, in this case using germanium lenses, which are suited to the wavelength, some further condensing optics, an interference filter, and a detector. The extra idea here is to include a cell of the target gas in the optical path to measure the signal with and without the gas, and to take the difference. The effect on the signal is as if the filter had a passband shaped like the carbon dioxide spectrum, so mostly avoiding emission from other molecules. It had a view along the track in the same way as IRIS and SIRS. This kind of instrument flew on Nimbus 4, Nimbus 5 and Nimbus 6 with different arrangements for selective chopping. Nimbus 4, with the oscillating mirror, also had a window channel at 12 microns. Nimbus 5, as well as carbon dioxide, had 8 channels for water vapor and cloud detection. And the selective chopping in this case was done by moving the gas cells rather than the mirror. Nimbus 6 pressure modulator radiometer used Doppler shift between the spacecraft and the atmosphere, using a long track angular scanning for field of view compensation to effectively scan across a spectral line. In this case, the selective chopping was by just moving the gas, by modulating its pressure. This did a reasonable job of producing vertical profiles up to somewhat greater height. This plot also shows a temperature distribution from 80 south to 80 north, to up to around 1 millibar. We also saw the first southern hemisphere warming to be seen from space. The Met Office took up the pressure modulator idea and provided the stratospheric sounding unit, SSU, for the American operational satellites, TIROS-N and NOAA 8 to 14. And gas correlation was subsequently used by several different instruments, including Vortex on Pioneer Venus in 1978 and several others. I daren't press it again because it'll move on. Nimbus 5 also had a more straightforward filter radiometer, ITPR, the infrared temperature profile radiometer. Cross-track scanning was a feature here, imaging the temperature fields horizontally. This was also used on later instruments. VTPR, the vertical temperature profile radiometer, and HERS, high-resolution infrared sounder. Further versions of HERS flew on NOAA 6 to 19 as part of TOVS, the TIROS operational vertical sounder, which comprised HERS, SSU, and MSU, a microwave sounding unit. This shows the scan pattern of ITPR compared up here, 3 blocks on subsequent orbits, compared with the pattern for SCR and for the microwave spectrometer. And this illustrates how satellite data might have improved an analysis in 1973. The solid lines are the NMC objective analysis based on conventional data for that day. The unreadable numbers are the ITPR, these little dots, are the ITPR 500 millibar temperature retrieval, and the dashed lines are, I think, a manual adjustment to the contours to agree with the ITPR data. This isn't the right way to do it, but it does give an indication as to the improvement that might be possible where conventional data was sparse. A modern assimilation may well have produced a different result, of course. Subsequent instruments of this kind improved the resolution still further. This is VTPR, and HERS has up to 42 fields of view across the track. Nimbus E microwave spectrometer also flew on Nimbus 5. This was a straightforward microwave receiver pointing downwards with a field of view of around 190 kilometers. Planck function is proportional to temperature in this spectral region, which is a mild advantage, making the radiative transfer more linear in temperature. But clouds are almost transparent in the microwave, and this is a major advantage. It had only 3 channels in the oxygen band near 5 millimeters for temperature. It also had a couple of channels for water vapor. I've not made a note of where they were, but there are water vapor spectral lines everywhere. This radiosonde comparison shows how the fine structure you see in radiosondes isn't seen by the microwave spectrometer, but nevertheless this is a proof of concept. It was followed by much more capable instruments as the technology improved. SCAMS, Scanning Microwave Spectrometer on Nimbus 6, was a cross-track version of NIMS with 13 angles, nadir and 6 either side of nadir. That was followed by MSU, a Scanning Microwave Sounder Unit, which was part of the operational system TOVS. The MSU on Tyros N had 4 channels in the oxygen band and apparently no water vapor channels, and 11 views cross-track. TOVS flew on Tyros N in 1978 on the subsequent NOAA series, and this plot shows the scan pattern for HERS and for MSU, not for SSU, which I think was just a nadir track. The ovals are MSU. These tiny dots are HERS. And showing that by this stage we're getting more or less global coverage with satellite sounding for temperature. For Nimbus 6 we have a new idea. This is limb sounding. The limb can give much better vertical resolution. It is viewing horizontally from the spacecraft through the atmosphere. The vertical resolution is determined more by the geometrical field of view, not so much by the physics of the radiative transfer, as you can see in this plot of weighting functions where you have a big spike at the tangent point. But better resolution requires a smaller field of view, and hence less signal, so better detectors are needed. So LRIR used cooling, which improves detector noise, to make it much more sensitive. The detector was cooled by ammonia and methane dewars, so it had a finite life. LRIR had channels for temperature in carbon dioxide and for ozone and water. There is a disadvantage. Looking through the limb, you're much more likely to see clouds in the troposphere, so you hardly ever see anything below the tropopause. This comparison with a combination of radiosonde and rocket sonde shows the extent to which limb sounding can follow the finer structure of the profile. The solid line is the rocket sonde and radiosonde combination. The circles are the limb retrieval. LIMS retrieval. LIMS was the improved version of LRIR. LIMS flew on Nimbus 7, and this illustrates the kind of data that we could get at that stage. The top one is a cross-section of temperature, zonal mean cross-section, and the bottom one is a zonal mean cross-section of ozone from around 100 millibars to around 0.01 millibars. This is nitric acid as seen by LIMS, illustrating that a colour plot looks much prettier. Limb sounding was followed by several instruments following LRIR. Nimbus 7 had 2 limb sounders, LIMS from NCAR and SAMS from Oxford. On URs in 1991, almost all the instruments were limb sounders. And on Envisat in 2002, there was a high spectral resolution Fourier transform spectrometer, MIPAS, and Skiamachi, which was a solar spectrometer, which had fields of view which could look at both media and limb. URs was launched in September 1991 and had a lot of limb sounders. Clay's involved a tunable etalon as a spectral device, and the whole of the instrument was inside a dewar. Halo used solar occultation and gas correlation radiometer to measure things like hydrogen, HCl and HF, and other gases. ISAMS was an improved version of SAMS, MLS, microwave limb sounder. Windy was a limb interferometer measuring Doppler shift of air glow lines, looking at the thermosphere and mesosphere. And Hardy was a Doppler, high-resolution Doppler imager, also measuring wind. The UR's team hadn't planned for this kind of event. Mount Pinatubo went off a couple of months before we launched, and this eruption penetrated well into the stratosphere. MLS, Windy and Hardy were not really affected, but Clay's Halo and ISAMS all saw this cloud, which went to quite high levels. Come on. Try again. The ISAMS window channel gave us the possibility of tracking the evolution of the cloud for many months. Notably, even though the volcano was at 15 degrees north, the cloud had moved towards the equator and was travelling downwards towards both poles. These are plots for October, November, January and April 92. Also on Nimbus 7 was the first solar occultation sounder I can find, SAM2. Solar occultation has the advantage of a strong signal, but disadvantage of poor coverage. SAM2 and SAGE were complementary instruments, meant to be launched at round about the same time. SAM2 was a single-channel instrument looking at the Sun around 1 micron on Nimbus 7. And Nimbus 7 was in a sun-synchronous orbit from 80 south to 80 north, so it only saw high-latitude aerosols, such as polar stratospheric clouds. SAGE was a dedicated spacecraft in a precessing orbit which saw a range of latitudes between 72 north and south. It had 4 channels centered at 1, 0.6, 0.45 and 0.385 microns. On the left, we see aerosol profiles before and after the Mount St. Helens eruption. And it was possible to follow the evolution of the aerosol over several months. On the right, the plot on the right is from SAGE. It's based on measurements over 5 weeks as the precession of the orbit moved the measurement latitude southwards. Solar occultation was taken up by several subsequent instruments. ATMOS was a Space Lab mission of only a few days, a high-resolution spectrometer. Halo on URs was partly gas correlation radiometer, targeting stratospheric chemistry. ACE is a dedicated Fourier transform spectrometer in a polar orbit. And Skiamachi, I think I've mentioned already, is a visible and ultraviolet instrument. Next comes radio occultation. This has been used since the early days of planetary flybys to measure atmospheric density. For example, on Mariner 4 Mars in 1965 and subsequent Mariners. The phase delay of the radio transmission from a satellite received on Earth is measured and interpreted in terms of the density of the atmosphere. GPS itself started around 1973, but GPS radio occultation wasn't demonstrated until 1995. It measures the phase delay in the signal from a GPS satellite and the receiver as the GPS satellite rises or sets. It can be interpreted as a density profile and hence as a temperature profile. I haven't been able to find who first thought of the GPS satellites for this purpose. The earliest references in the literature seem to be around 1992, but at that time it seems to have been a fairly established idea. There was a suggestion by Lusignan et al. As far back as 1969 to use a pair of satellites for this purpose, and that was before GPS satellites had been developed. I've put Rick Anthony's photo on this slide because I can't find the originator, because he appears to have been instrumental in getting the first satellite data first satellite test GPS MET implemented. The first flight was on a small experimental satellite in 1995 and was very successful. The cylindrical body is only 1 meter across and 38 centimeters thick. And the GPS instrument is this little box here, which is hardly any bigger than a mobile phone. This is the first radio occultation sounding on the first test flight, and it appears to have been very successful. The resolution appears to be excellent, but I'm not entirely sure that the radiosonde and the standard atmosphere, also plotted, are correctly labelled. Surely the standard atmosphere ought to be the one that goes up to the top. COSMIC series is a collaboration between US agencies and Taiwan's National Space Organization. 6 microsatellites forming COSMIC 1 were launched in 2006, and they're still operating. COSMIC 2 constellation was launched in June of this year. This slide shows typical daily coverage of COSMIC 2 compared with radiosondes. Many more GPS instruments have been launched or are planned, and this has become an important data source for weather analysis. And most recently, GOMOS, Global Ozone Monitoring by Occultation of Stars, was a bright idea. GOMOS was a medium-resolution spectrometer covering the wavelength range from 250 to 950 nanometers, with a telescope of about 20 by 30 centimeters. It can measure profiles of ozone, NO2, NO3, O2, water, aerosols, temperature, using many target stars, so it has many opportunities to make measurements, just like GPS. Stellar occultation gives coverage day and night, where scattered solar UV gives day coverage only. This illustration shows ozone cross-section for 4 separate winter seasons, illustrating a secondary peak up here at high latitudes and high altitudes in the polar regions. This gives a reasonable qualitative fit to the whole atmosphere community climate model provided by NCAR, which includes interactive chemistry and ions and electrons. Beyond this point, there have been many more satellite instruments and technical improvements, better detectors, etc. But I've not noticed any major innovations in methods. What I want to do now is to move on to data processing and understanding just what the data means. Making measurements is only part of the exercise. You then need to interpret what you measure in terms of what you really want to know. Data analysis started simply in the early days, became more complex as understanding grew and as computers became more capable. Those of us working on temperature sounding mostly started by noting that the equation of radiative transfer is linear in the Planck function, and the CO2 amount is proportional to pressure. We aimed at solving the Planck function versus log p rather than temperature versus height to make the equations as linear as possible. We represented the atmosphere as, for example, n layers or n polynomial coefficients for measurements at n wavelengths and solved linear equations. And we soon discovered that the results for realistic situations looked nothing like the real temperature profile. This is an illustrative simulation of what happens. The solid line is a nominal temperature profile. The dotted line is an exact retrieval using a degree 7 polynomial, so 8 coefficients. And I used an idealized 8-channel radiometer. The dashed line is the same, but with a small amount of random noise added. The dotted line sort of vaguely fits the nominal temperature profile. The dashed line is nothing like it. Clearly, this is not a good way of doing it. Various kinds of ad hoc approaches were tried. For example, fewer levels and channels and the least squares fit. But there was no logical way to choose the number of parameters or the profile representation. In 1963, Sean Toomey applied an approach of Phillips, which he generalized and simplified. I won't trouble you with the algebra, it'll take too long. What he did was to do a constrained least squares fit, where the added constraint controlled the smoothness of the profile. The number of levels in the profile is no longer limited to the number of measurements. It could be larger or smaller. This also gives you a fudge factor which you can adjust to determine either the smoothness of the profile or the accuracy of the fit to the measurements. Tikhonov published a similar approach in the Russian literature also in 1963. A few years later, Karl Mathieu looked at the problem from a different angle to examine the information content of measurements. He looked at the empirical orthogonal functions or characteristic patterns of an ensemble of real measurements. He also looked at the singular vectors of the weighting functions. He found that there were only about 4 or 5 ways the Umkehr curve could vary. And this is the real reason why Hans Deutsch in 1957 couldn't solve for 9 layers, but could solve for 4 or 5. There really were only 4 or 5 independent pieces of information in his measurements. I think I'll skip this slide just to finish before 6 o'clock. Just to say, whoops, no, maybe I'll go back a bit. Karl Mathieu also looked at the singular vectors for the weighting functions and came to the same conclusion with that. The measurement method could only measure about 4 or 5 independent ways the ozone profile could vary, however the profile varied. In this case, the singular vector is the measurable pattern of variability, and a singular value is the sensitivity of the measurement to that pattern. He also explained how Sean Toomey's technique worked in terms of these vectors. Other research areas have similar problems. Geophysicists working on sounding the solid Earth using earthquake data have the same mathematical problems of solving ill-conditioned equations. From Backus and Gilbert, we got the concept of the averaging kernel, which expresses how the retrieved profile is related to the actual profile. They also investigated the optimization of resolution in the presence of noise. And they produced a paper in Phil Trans, which you can see from the number of pages there, is big, 70 pages, of dense mathematics. There were miscellaneous approaches to finding a solution. Lots of methods were proposed and investigated. if you want an exact solution to fit your measurements, the smoothest exact solution can be shown to be a linear combination of the weighting functions. There were various ad hoc relaxation methods, both linear and non-linear. There was direct multiple regression, compute radiances for a sample of atmospheres, do a linear regression between the computed radiances and the profiles, or take a coincident set of radiosondes and satellite measurements and do linear regressions between them. Onion peeling for limb sounding, working downwards from the top, and optimal estimation, combining the measured quantities with a properly characterized prior estimate using, for example, Bayes' theorem. All of these and others were aimed at finding a solution. What they do is select one from an infinite set of candidate profiles that could be a solution. I wrote a review in about 75 to try and put all of this onto a firm footing and clarify the characteristics of various methods and the relationships between them. I was pleased when a lot of people found it useful, and it's been frequently cited since. In the early 80s, I was encouraged, or maybe nagged, by Rod Jones, then a postdoc working on ISAMS data, now a professor in Cambridge, to take this further and do a formal error analysis and characterization of retrieval methods to help understanding. The result was a paper probably too complex to summarize here, but briefly, we characterize that set of profiles, for example, by means and error covariances, including separating errors into different types, by errors due to noise, due to smoothing, due to model, due to fixed parameters. The solution is some function of the true state, and we should understand that function. Linearized, this means averaging kernels and contribution functions. These ideas seem to have been taken up by the community, and recently a project has been set up under Spark to extend these ideas and make sure that everybody is doing things the same way. And finally, assimilation. This is too big a subject for me to say anything sensible about, and there are people in the audience here who know far more about it than I do. I refer you to a recent paper by John Eyre and his co-authors in the Quarterly Journal, in the recent Quarterly Journal. For many applications, the reason for making these measurements is to study the 3 or 4 dimensional state of the atmosphere for things like weather forecasting, climate studies. At first, retrieved profiles were treated as if they were radiosondes, and the results were not very satisfactory, and for many years satellite measurements were treated with suspicion by meteorologists, and to some extent only used if they agreed with the analysis. They aren't like radiosondes because of correlated errors and because of the finite field of view. A retrieval is not a good interface between satellite measurements and assimilation unless the full error characterization, including covariance matrices, is used. But from around about 1990, there was a move to direct assimilation of radiances, which has led to major improvements, together with, since around about 2000, the increasing availability of different types of satellite data. This shows the number of satellite data products monitored by the European Centre since 1996. And you can see that it has been increasing dramatically since around about 2000. A century of progress. I haven't lived through it all, and it sometimes feels like that. When I started, there were no satellite sounders at all. There were a few satellites. At that time, Gordon Dobson was still alive and active, And my PhD research supervisor, Desmond Walshaw, had worked with him in his younger days. And now it's a big and important subject that I've been privileged to be a part of. Thank you.
Thank you very much, Clive. Do you want to answer any questions that people
I could try.
Are there any questions for Clive?
Clive, you pointed out that satellite measurements were not terribly welcome to meteorologists in the early days. They didn't really think they helped very much, as I recall. And then gradually they became a really important part, of course, of forecasting as they are now. What I'm noticing is a bit of a parallel now with the obsession on, a very justified obsession on global change and warming. The satellites are getting a bad press again as to whether they're really telling us very much about that or in a reliable way. Or wondered if you had any sort of thoughts about that. Having been through all this, now the modern era is tackling this new problem using satellites, do you think?
Not really. This is something I haven't been following.
It's not resolved yet, of course, so it's
No,
a bit of a trick question.
Yes.
Clive, in one of your slides, you said not much was happening, I think, over the southern hemisphere or something, but there was a big stratospheric warming, maybe 2 months, 3 months ago, maybe.
Yes, but that's all gone.
That's all gone.
Yes, I just took that from the appropriate website as to the measurements of ozone 2 days ago at various levels, and it looks pretty symmetric. The northern hemisphere looks even more symmetric.
You only had about one Russian reference. I mean, the Russians.
Oh, the Russians did a lot, yes, but
they have quite a mathematical approach to it. I just wondered what.
Well, I didn't really have time to. There's a lot more than what I've been able to present in my time.
Did you collaborate with the Russians?
Not very much. No, we should have done.
I mean,
We knew about what they were doing.
I know about. I mean, the Russian work was fantastically important for intelligence.
Well, thank you very much, Clive.
Thank you.
Is everything just on the computer, is it? So we make our way to the
Yes.
nightclub dinner, which is Paul.